Which one of the following is the correct term for the gravitational force the Earth exerts on any object on or near its surface? This very same question was there in the June examination, and the answer is A. Weight. Weight is the gravitational force that the Earth exerts on any object on or near its surface. It's just one of those definitions that we overlook, but look at 1.1. You needed to know what weight is. Let's go ahead and do 1.2. The driver of a truck places a suitcase on the level dashboard in front of him. He observes that the suitcase is sliding towards the windscreen. At the instance, the truck is probably moving. Okay, so we're supposed to choose between a few options there. We have our dashboard, which is level, and there's a suitcase on top of the dashboard. The suitcase is sliding towards the windscreen. Why do we keep our seat belts on in the car? So that when we experience inertia, there is something holding us back. The suitcase is experiencing inertia. It wants to keep moving at the very same speed that it was moving in. That tells us that the car is slowing down. That is why the suitcase is moving forward. If the suitcase was moving backwards, then the car will be starting to speed up. So the answer to 1.2, we have forward and slowing down. The car is moving forward, but it is slowing down. Our suitcase is experiencing inertia. So the answer to 1.2 is C. 1.3. A stone is thrown vertically upwards. Which one of the following combinations correctly represents the stone's acceleration and velocity 1 second before reaching maximum height? Assume that air resistance is ignored. Usually, we are interested at maximum height, but now we are interested at 1 second before the maximum height. Before I even look at the options, I know that the acceleration is 9.8 meters per second squared downwards. That is not up for negotiation. So option B and option D is the only two options I'm looking at. Now let's think about the velocity. Well, our object is thrown vertically upwards. So before it reaches maximum height, it must still be moving upwards. At B, we have 9.8 meters per second upwards, and at D, we have 9.8 meters per second downwards. We know obviously that our answer is gonna be B. Our object is still moving upwards. It hasn't reached its maximum height. But you can also get to B being the answer using another thought process than the one I'm using. Yeah, I have it in my head, but I'm just going to keep it to myself. Let's move to 1.4. We have 1.4. A car approaches a road with a lower speed limit, and the driver slows down the car. The two vectors, momentum initial and momentum final below, represent its initial and final momentum respectively. Initial and final. Which one of the following vector diagram correctly represents the change in momentum of the car? A lot of people will probably think that P initial and P final are pointing in the same direction. So I can just add them and my answer will be A. But that is not the case. We're looking for the vector that represent the change in momentum. P final minus P initial. So let's go ahead and have that. For P final, the vector looks something like this. This is P final, and we're supposed to subtract P initial to find the change in momentum. So if we do that using the tail to head method, we're going to have something that looks like this. This is our P initial. This is our P final. And here is where we have our change in momentum. Clearly, the answer is D. Let's move to 1.5. So what do we have in 1.5? An object is dropped from a height h above the ground. Dropped, what does that tell us? Vi is equals to 0. Let's carry on. Which one of the following graph best represents the relationship between its kinetic energy and its height above ground level. Let's think about that. At our maximum height, v is equals to 0 meters per second, because our object is just getting dropped at maximum height. And when the height is equals to 0, our object is striking the ground. So we have v max. Without even looking at the options, we can deduce this just from vertical projectile motion. So let's try find a graph that supports what we are saying, which we know to be true. Here, as the height is increasing, the kinetic energy is increasing. This cannot be true. When the height is increasing, we need our kinetic energy to be decreasing because v is equals to 0 at the maximum height. If we look at option A, when the height is at its maximum, we have a kinetic energy of 0. So v is equals to 0. Let's look at when the height is equals to 0. Do we have maximum kinetic energy? When the height is 0, you can clearly see that we have maximum kinetic energy. I don't think we have to look any further. It seems like our answer here is A. Let's go ahead and do 1.6. 1.6, how does the wavelength and frequency of a wave source change when it moves towards the observer? That's quite an easy one. When an object is moving, a sound source is moving towards an observer, the wavelength is going to decrease and the frequency is going to increase. So that is the option we're looking for. Wavelength decrease, frequency increase. So option B, the answer to 1.6. Our wavelength is going to decrease and our frequency is going to increase. 1.7. 1.7. A positive point charge Q1 and a negative point charge Q2 of equal magnitudes are held at fixed positions, as shown in the diagram below. So Q1 is positive and Q2 is negative. I need to put that there so that I don't forget. S is exactly halfway between Q1 and Q2. I don't see any S on the diagram, but maybe they are referring to Y. Let's see, which one of the following combinations gives the correct direction of the net electric field due to the presence of charges Q1, Q2 at positions X, Y, and Z respectively. So when we have a point charge, we can always assume that it is positive. So let's put that there and do some analysis. First, let's look at X. There's a repulsion between X and Q1. So the electric field is pointing to the left. Between Q2 and X, there is attraction. But look at how far Q2 is. The electric field is inversely proportional to the distance between the charge and the point of interest. So Q1 is going to win this battle. At point X, the net electric field is going to be pointing to the left. So we are only looking at option C and option D. Let's go to Y. How is Q1 and Y interacting? Q1 is going to be pushing to the right. They're all positive. So there's a repulsion. And then Q2 and Y, they have opposite charges. There's a force of attraction. So Q2 is also pushing to the right. So at point Y, the net electric field is to the right. No questions asked there. So which option? C and D, they are still all correct. Now we have to move to Z, our position Z. Let's see what happens at Z. Z is positive, Q2 is negative. There is an attraction there. So the electric field is to the left. Now let's look at Q1 and Z. Well, Q1 is too far. So we can just pay attention to the effect of Q2. That is only because they have equal magnitudes. If they had different magnitudes, then our question will be a bit more difficult and we would have to actually consider the distances and the magnitudes in detail. So Z is moving to the left. That is option D. So the answer to 1.7 is D. Let's go to 1.8 and hear stories. So in 1.8, in the given circuit diagram below, the three light bulbs L1, L2, and L3 are identical. X, Y, and Z are readings on the ammeters in the circuit. Which one of the following mathematical equations is correct? Let's do some analysis. Well, what I'm realizing very quick is that at X, we have total current. So this is IT. Our three bulbs are identical. So the current is divided proportionally. The reading on Y is equals to the reading on Z. We don't have a reading on L1, but I don't think that will hinder us to reach a conclusion. Let's look at what makes sense. A says that the reading on Y is equals to X minus Z. Well, that is not true. The reading on Y can be equals to X minus 2Z, not X minus Z. And B, the reading on X, the total current, is equals to 3 multiplied by Y. Here on this path we have Y, here on this path we have Y, and here on this path we have Y. Z and Y are equals to each other. So this is true. Option B is true. So the answer to 1.8 is B. That is true. 1.9, the solid line in the graph below represents the output of an AC generator. The dotted line represents the output of the same generator after a change has been made to the generator. Okay, let's go ahead and do some analysis. Before the change, we have 1, 2. We have 2 rotations, and after the change, we only have 1 rotation per unit time for the same amount of time. So what has changed? Our speed of rotation has now been halved. Which option is that? C. So the answer to 1.9 is C. And 1.10, the diagram below indicates an energy level diagram that corresponds with the 4 energy levels in an atom. Which one of the 4 energy transition has the shortest wavelength? Shortest wavelength or highest frequency. The higher the frequency, the higher the energy. S. Option D.